Hello students, this is your ENGR 433 Machine Design Midterm Exam Study Practice, where we cover the topics of shafts, bearings, and gears. Very briefly, the example problem that we went through had these 9 parts to the question. You can read through those. We've got 3 graphics here. On the far left, you have a graphic that shows each of the gears from the side view, and then in the center, you have the top view of each of the gears where one of the gear has been rotated down so that we can see them all laid out flat in relation to each other in one page. And then on the right, you see the breakdown of all the forces on the bearings and the gears. Those are the forces that we're going to use to perform these calculations. Assuming A is the input shaft, calculate the input and output torque. So the gear on the input shaft, you see it's the very small one. It has 16 teeth with a module 2 millimeters. Don't forget the module means diameter per tooth. Diameter of the gear per tooth. Therefore, the radius is 16 millimeters. And so the input torque is 1314. If you look over at the load diagram, you see that 1314 is tangential force. I even annotated that as tangential force. 1314 times that 16 millimeter radius gives you 21,000 Newton millimeters, so that's 21 Newton meters. And the output shaft up there on the top right, you see shaft C has 60 teeth. So the gear on the output shaft has 60 teeth, and it has a module of 3.2 millimeters. So we have 2 different modules for these 2 different meshes in this gear train. So the upper module there is 3.2 millimeters, and therefore the radius is 60 teeth times 3.2 divided by 2, 96 millimeters. So the output torque is 3280 times 96, that's 315 Newton meters. Based on an input torque of 21 Newton meters and an output torque of 315 Newton meters, I could divide 315 by 21 and find that the gear train ratio is 15. So there we go, there's the train ratio equals T output over T input, 315 over 21, that's 15. 3. Assuming the input RPM is 1200 RPM, what is the output? We just calculated the train ratio, so 1200 RPM divided by 15, the output must be 80 RPM. So in this problem, we are reducing the RPMs and we're increasing the torque, or whatever we're using this machine to do. Calculate the center distances. So the center distances depend on the number of teeth, of course, because the diameter depends on the number of teeth, and the module. And don't forget we have 2 different modules here. So the center distance for the mesh between shaft A and shaft B, half of diameter A and half of diameter of that gear on shaft B that it's meshing with. So you see that's 16 times that module of 2 plus 80 times that module of 2, divide both those by 2, so 80 plus 16 is 96. And then the shafts B to C, we have a module of 3.2, so we have the 20 teeth times 3.2 module divided by 2 plus the 60 teeth times 3.2 module divided by 2, and we get 128 millimeters for that B to C center distance. Then we're asked to draw the vertical and horizontal bending moment diagrams for shaft C and calculate the resulting max bending moment. So we start with the vertical shear force diagram. You see we have a load of 113, then we go across 3 centimeters, which is 30 millimeters, and we have an upward load of 1,530. Then we go across the rest of the shaft and it goes back down to 0. So you can see the max bending moment from that force is going to be 1,113 times 30 to get 33,390 Newton millimeters. So that's 33.4 Newton meters, which is the same as kilonewton millimeters. You do the exact same thing for the horizontal, and you can start to catch the pattern here on how to calculate the maximum bending moment. There, it's going to be the maximum bending moment is going to be the reaction load at the bearing times the distance that you go across to that gear. So the max bending moment for the horizontal is 2385 times 30 millimeters. That's 71.5 Newton meters. And the resultant is going to be the square root of each of those squared. So the square root of 33.4 squared plus 71.5 squared, and that is 78.9 Newton meters. Then number 6, which shaft should have the largest diameter? Well, we already started to look at what are the bending moments for the shafts. We started with shaft C, and the calculation approach is going to be the same. So we can rank the shafts in terms of torque and bending moment. Shaft C has a torque of 315 Newton meters, a bending moment of 78.9. Shaft B, we use the gear ratio between the two, so it has 1/3 of the torque of shaft C, and it has a bending moment. We can use the same approach, go across the 30 centimeters you see there, or 30 millimeters, and apply that load across that distance of 30 millimeters, square that, plus the other plane, the 2274 newtons times the 30 millimeters, and square that, and we can get the bending moment at that location, 73.1 Newton meters. And then shaft A has a torque of 21 Newton meters. We calculated that already. Using the same approach, we can slide all the way across from the 239 newtons and the 111 newtons across that 90 millimeters, square both of those, we can get the resultant bending moment at that location where the gear is located. So the torque and bending moments for shaft B and A are less than shaft C, so shaft C should have the largest diameter. Now I'm not expecting to do this for the midterm exam, but we can go a lot deeper and calculate a first approximation based on some reasonable assumptions of what those diameters should be. So I went ahead and tried to do shaft C and found that a diameter of around 30 millimeters, 33.3 millimeters, was a good starting place for the diameter of that shaft. The next thing that we need to solve for is which bearing locations receive the most damaging combinations of load and cycles. So this involves some more critical thinking. Damage to a bearing depends on the level of the load. We can see where the highest load is exactly here. We look at the bearings. There's bearings at locations A, B, C, D, E, and F. And I see all the loads there, and I see that the highest load location is the highest load location. But what about cycles? In terms of cycles, I have a train ratio, don't forget, of 15. So going from shaft A, where I have 1200 RPM, to shaft B, I have 1/5 of the RPM. I have 2400 RPM. To shaft C, I only have 80 RPM. So the 1200 RPM has 15 times the number of cycles, the most damaging. So digging deeper from our critical thinking from number 7, number 8, we actually have to solve this now. No, we don't have an application factor in here. We're just using the base approach. We're not modifying the reliability based on Weibull distribution for 90% reliability, and we've got an exceptionally long life that we're looking for here. So that's how we're building in more reliability in this case, because we're asking for 5 years of continuous use. So if you calculate 5 years, that's 8,760 hours per year. So 5 times 8760, and then there's 60 minutes per hour. So that's 5 times 8760 times 60, and that gives you 2,628,000 minutes of use that you're looking for. So in the first shaft, shaft A, if we need 1200 RPMs, multiply that by 2,628,000, that's 3,154 times 10 to the 6th revolutions. And you see I calculated shaft CBA there, so they go in the order from top to bottom: 210 times 10 to the 6th, 630 times 10 to the 6th, and 3154 times 10 to the 6th. The 10 to the 6th is handy to leave in there because the L10, the bottom of our fraction, is going to be 10 to the 6th. So I can just cancel the 10 to the 6th and take the remaining value times 1/3 power. Note that 1/3 is the cube root. So I can also use the cube root function when I'm solving for ball bearings on my calculator, and that might save time as well. For roller bearings, the A factor would be 10/3, but for ball bearings, A equals 3, so it's the cube root. And then we need to find the resulting force on each bearing. Bearing E there is square root of 2.385 squared plus 1.113 squared, so that's 2.63 kilonewtons. Solve for the resultant force the same way for bearings C and B. And then we can find the catalog values that we need to look for by solving the equation that's at the very top in the solution. So C10 equals F sub D times L sub D over L10 to the 1 over A. So I've calculated each of those for bearing E on shaft C, 2.63 times the cube root of 210, that's 15.6 kilonewtons, and so on for the other bearings on the other shafts. And it was not clear before we did the math, but after doing the math, you can see that the bearing that has the most difficult position in terms of the combination of load and the number of cycles is bearing C on shaft B. So you need to look for a 20.9 kilonewton deep groove ball bearing. I looked on the internet and I found the SKF 206 deep groove ball bearing has a bore diameter of 30, which is pretty close to what we need, and it has a dynamic load rating of 20.9 kilonewtons. That looks like that's the right bearing for us. Finally here, making reasonable assumptions, what should be the face width of the output gear? I have simplified this immensely. You still have to plug in your brain cells, but this is much simpler than the most complicated approaches from the Shigley's textbook. So we'll perform the calculations for the smaller gear in the mesh because this approach is usually more conservative by looking at the smaller gear instead of the larger gear in the mesh. And we're going to use the location with the highest load. So we're going to start with that WT mod for the gear, the output gear. And we're going to just assume an overload factor for light shock, power, and moderate shock. You see in the upper right, the diagram, so a K sub 0 of 1.5. We're going to assume a moderate dynamic factor of 1.4. We're making an initial guess of the face width of those gear teeth of 40% of that smaller gear diameter. And so that's 0.4 d sub p. Plug that into the size factor equation, K sub s. K sub s equals 1 plus that face width over 10 d sub p, so the d sub p's cancel, you get 1.04. Then for commercially enclosed gears with uncrowned teeth, K sub m equals, and I made some simplifying assumptions, 1.5 plus C sub pf plus C sub pm, or C sub pf for the gears smaller than 430 millimeter face size, and we already said ours is what we're looking at is going to be 40% of d sub p, so that's 40% of 64 millimeters, which is an initial assumption of 25.6 millimeters, and we'll see later on if that assumption is actually similar to, quite a bit different from our calculated value. Technically, we should iterate on this. If we solve for a face width that's different than 25.6 moment, I'm not going to iterate on it depending on what we get. So we'll see what we get. So you plug in the C sub PF and you get 0.175. C sub PM has two possible values. One, it equals 1 if the gear is perfectly centered on the between the two bearings. Now we can already tell that our output gear is not perfectly centered, and so I plugged in the geometry values between the two bearings. It is 3 plus 8 centimeters, so that's 11 centimeters total. And then between the center and where the gear is, it's 2.5 centimeters. So plug those values in, that's S1 divided by S. 2.5 divided by 11 is 0.227, which is greater than 0.175, which means you have to take a little hit on the C sub PM factor, and it's going to be 1.1. So K sub M equals 1.5 plus 0.175 times 1.1, so that's 1.69. So the modified transmitted load is going to be the transmitted load, which is 3.28 kilonewtons, times the K0, Kv, Ks, Km, which turns out to be 12,100 newtons. Then we can use that value to use the two approaches to calculate the minimum face width. First is from the bending stress, and second is from the contact stress. We're going to hit them both with a safety factor of 1.5. We're assuming for the bending stress that the steel has a tensile strength of 400 megapascals. So we plug all that in, but we're missing one value, and that is on the next slide, which is Y sub j. I'm going to finish the explanation for this slide, but you need to look at the next slide to see where that Y sub j comes from. That's the Lewis form factor in combination with the stress concentration factors for those gear teeth roots. Okay, so we plug those values in, the 12,100 divided by the module, the 3.21 over, and then on the next slide you'll see where that 0.335 comes from, times the safety factor of 1.5 over the 400, the strength value, and we get 34 millimeters. Now that's bigger than the assumed 25.6 millimeters. So we should iterate, but first we need to check what should our minimum face width be based on contact stress first before we decide to iterate. So we plug the factors for the equation that we need there. We're going to use a ZE equals 191 root MPa. That's the elastic interaction value for steel on steel for those gear teeth. And then an S sub C, so a contact strength of 1,400 megapascals. The contact strength is usually higher than the tensile strength, so that's the 1,400 is quite a bit higher than the 400 megapascals from the bending stress equation. There's one more thing you see over on the right, the geometry factor, and these are actually gear teeth with a 25-degree angle, not the normal 20-degree angle gear teeth that we're used to. So it's a little bit different, but that value is given, so you can just plug it in. And then the number of teeth on the gear is 60, number of teeth on the pinion is 20, so that's 3. So cosine 25 times sine 25 over 2 times 3/4 is 0.144. Plug that value into the equation along with the rest of the values, and you get a face width of 55 millimeters. So since 55 is greater than 34, it looks like our issue with these gears is going to be pitting. So that's why the contact stress is defining the gear tooth size. Pitting is going to be a bigger problem than bending stress apparently. And so 55 should be our minimum face width, and since that's over twice as much as the original assumption, 25.6, we should probably iterate and recalculate KS and KM and then come back through and recalculate the face width, and that wouldn't be very hard to do, and that would modify that value. So that is the final answer. If we don't iterate, 55 millimeters is the final answer for the gear width. And the only thing that we skipped over in the next slide is that Lewis form factor 0.355, the y sub j. So here's where the y sub j comes from. It's read off the chart. You take the number of teeth for which the geometry factor is desired. It was the smaller gear with 20 teeth in our case, and then go up to the curve for the number of teeth in the mating gear, and so that's 60 teeth. So go up to the curve for 60 teeth and you get a value of about 0.335.